All right. Hey guys, welcome back to lecture 15 of Mathematics of Data Models. This is a Northeastern University course, CS 2810, and I am Professor Wu. So in the past, we have been basically focused on linear algebra. And and with linear algebra, we like kind of concluded it for the last class. Now this time, from now on, we're going to shift gears and start working on something completely different, which is probability. Now, probability has its own like symbols and notations and representations, so and concepts. So today we're going to start by introducing the notations and the most basic concept. Now, the fundamental concept with probability is probably the probability mass or the probability density function. The idea is really simple. It's a function where you put in the event and it will tell you the likelihood of that event. Okay. Now, in probability, the symbols such as x and x have different meanings. In linear algebra, right, we learned previously that x is a vector or a variable. Capital X we use to represent matrices. Now, in probability, X is now one or multiple events that happen, something that happened, past tense, happen. Now, X is a random event that a lot of things could happen. So, this is something that happened. This is something that a set of things that could happen. So this hasn't happened yet. Now we use capital P or lowercase to represent this function. For example, if you may see that what is the probability? So again, remember, x is a set of possible events. So x is like something that's happening, and lowercase x is what happened. So let's say election. This is the election, and this is that person A won. Okay, so the probability that out of the election, the result was that person A won is 0.25. That's what these like notation is telling you. Okay, so you want to see this. You want to see this as one way to write probability. Now another way is to write it this way, or sometimes people just write P of x. This basically, what is the probability that x happen or would happen? Okay, so again, x is something that happened, past tense, happened. So the notation are different. Okay, now P of x here is saying that the probability that x happened is 0.25 out of 1. P of x is a function where you plug in the event. So you plug the event in and spits out the probability of it happening. All right, these functions, P of x, are called PMF, probability mass function, or density function, PMF of PDF. So probability mass, probability density. This notation is used more often. Right? We tend to just write PMF and PDF. And normally, you will see this notation and not see this notation. Now, the difference between PMF and PDF, right, why are there two kinds, is that PMF is for data that are discrete. So if you have data like coin flip, right, what is the probability of heads versus tail? So that's discrete, like two events. Now PDF are for continuous. So let's say you have something that looks like a bell curve, your SAT score. So in this case, here's the SAT score, and you can have a lot of numbers all in between. Examples of PMF function would be something like this. So here is an example data. that, for example, you roll the die 5 times, right? And these are the numbers you got. So this is the result of rolling a die 1, 2, 3, 4, 5 times. Now, based on this result, you can use the data and come up with your own probability mass function. Based on this result, you will get probability that x is equal to 1. So when you roll a die, the probability you get a 1 is 2 out of 5, because there are 2 out of 5 total events. And then the probability that you'll get a 2 is 0, based on the data. And the probability you get a 3 is 1/5, right? 1 out of 5. Probability you get a 4 is twice, 2 out of 5. 5 and 6 both got 0. So, I mean, if it's a fair die, you know it's supposed to be 1, 6, 1, 6, 1, 6. But we only rolled it 5 times. So, based on the data, you can just come up with your own probability mass function. Or simply, we can also write, instead of this like complicated big notation, just say the probability of 1 is 2/5, right? Probability of 2 is 0/5. So both notations could be used, but of course, since this is easier, we tend to write it this way. From this, right, you can even look at it from the chart, right? With the chart, you can just say, this is 2.5. So 0.25, 0.25, 0.5. Right? So here's the chart. This chart is called a histogram. And from this chart, you can read it and essentially come to the conclusion of what the probability of various events are. Now, that was probability mass function for discrete. Probability density function is now a continuous line. So this particular example is the line follows a particular equation. So the equation is a line looking like this, and it goes from 0 to 2, 0 to 2. And then it says it's 0 everywhere else. So it's over here is 0, everywhere else here is 0. That's what this equation is telling you. Now, based on this, right, and this could be the amount of time you need to spend studying, because the amount of time is not a countable number. It could be 1.5554 seconds. And that's why this would be like a continuous thing. Now, to find a probability with continuous, you need to find the interval. So what is the probability you need to spend 1 to 2 hours to study in order to do well, right? So you would need to know the area of this. To find the area, you essentially take the integral. So the integral tells you the area under the curve. So you take the integral of the probability. Here's the probability. You take the integral from 1 to 2, and that will tell you the probability of that you would need to study between 1 to 2 hours every day. Well, let's do a really quick calculation. Why don't you pause the video? What is the probability of x equal to 1? Now, try to take the integral for this. So, x equals to 1, you will need the integral from 1 to 1, 0.5x dx, right? And the other one is, what is the probability from 0 to 1? So here's 0 to 1, 0.5x dx. And what is the probability from 0 to 2? 0 to 2. So 0.5x dx. So these are the three integrals that you will need to solve. So if you want to do it, pause the video, try yourself. Otherwise, we'll move on. So if I were to take the integral from 1 to 1, it would be 0, because it would be just the same number subtracting itself. That means that whenever you are just trying to find a particular point, the area has to be 0, because it's the height times the width. And in these cases, when the width is 0, right, because it's just a line, there's no surface area, There's no area. Without area, the probability must be 0. This particular case from 0 to 1, it's actually the area of the triangle, right? So you can take the integral, you get the area. The area is pretty easy to find. It's like 1 times 0.5 divided by 2, which is a quarter. So you can see it matches. I just used the area of a triangle this time, but in theory you should be using the integral. Now, the last one is from 0 to 2. Well, that is the entire thing. So if you're talking about the entire thing, then the probability always sums up to be 1. So 1 in this particular case represents 100%. Whenever you have probability mass or probability density function, the entire thing, if you add all the probabilities, it should be 100%, which is mathematically 1 for probability. Now, to find the integral is a pain. Like in this particular case, we just used a very simple integral. But I want to make sure that when you go out to work in other companies, you know how to take integrals. Well, one way to do it is this function in Python, right? You just put the function in, and then what you do is, once you have the integrand, you put it into this quad function, and then just take the integral from 0 to 1. Okay, so remember, that's what we're doing from 0 to 1. So this is the interval. And once you do that, voila, then you have the result. And remember, it was 0.25, 0.25. So I want you to just know the idea that you can find the probability by taking the integral. But, very often it will be, you can just use like Python to do integration for you. Now, why will we really want this function? Well, life is uncertain. Who's going to win the World Cup? Which companies you're going to work for? Are you going to be successful in life? These are all questions that, if we have probability density or probability mass function, would be really helpful. If it tells you that the probability you're going to work for, I don't know, a tech company or a biology company, right? If in high school somebody tells you the probability you're going to work in a biology company is 99%, you probably would major in biology instead of some tech. So knowing the probability mass or density function really allows you to make intelligent decisions. Okay, but nobody can predict the future, right? But when you have PDF of all the possible outcomes, you essentially can make the best decisions based on informed likelihood. Or you can make lots of money if you happen to pick the right stocks. Or just make general good life choices in general. If it tells you, well, the probability of you getting cancer if you smoke is very high, well, you should probably not do it. So much of data science, right, is basically understanding and model this uncertainty. So a lot of data science is you take the data, and from the data, you essentially find the probability density function, and then based on this, you make decisions, right? You can make decision based on it. So that's why we like to come up with these probability density, probability mass function. So today we're going to familiarize ourselves with the basic concepts, okay, of what we can do with these probability density mass function. So first, we need to realize that with these functions, right, life is complicated, and very often we need to take more than one factor into account, right? So it's not always just one variable. So for probability distributions, we can also consider multiple variables. So here's some examples of multivariate probability distribution. Like first, this is an example, right? So now you have two variables. You got to plug two things in. So it's not just probability x. Is what is the probability of x and y happening? Hmm? X and y. So over here, this one here is probability. What is the probability of x, y, and z happening? So now it doesn't have to be x, y, z. We can write it like what is the probability of x1, x2, and x3 happening? All right. So you can represent it different ways. Now, when you only have one variable, then that kind of depends on the context, because one variable can just mean a single variable. Like there's a one variable you're taking into account, or it could be a vector of variables. It could be really x, p of x, but x is really x1, x2, x3, x4. Right? X could be multiple variables. So depending on the context, when you have just one, it could be really just talking about one variable, or that could like be a representation of a vector of variables. So very often, if you only have a couple, like 2 or 3, you will write it like this. But if you have 100, it gets really cumbersome to write x all the way to 100. So you represent the whole thing as just p of x. And that's the reason why x could be both 1 or multiple. Okay? So, like I said previously, when we write x, p of xy, what it's really saying is that what is the probability of x and y happening? Okay? And these distributions that when you have multiple of them are called joint distributions, because you're joining multiple, you're like joining multiple variables together. So joint distribution. And the notation the alternative notation, you can put some logic into it, right? You can also say this p of x and y is also written probability that the event, out of all the possible events, x happen, and out of all the y events, y happen. Another way to say it is through the intersection symbol. So you can picture, here's a picture, like Venn diagram, and here's the intersection. So here's event x and event y. So you can see that the intersection is really x and y, right? So what it's saying here is what is the intersection of all the probabilities such that x is equal to x and y is equal to lowercase y. So this symbol here is for intersection. Okay? Alternative symbol, like intersection, is this way, but you can do an opposite one. So intersection is really and logic. But alternatively, this is a union symbol, union symbol, and it means or. You can think of that as the or logic. So we can write what is the probability of x happening and y happening, or y happening, or. Okay? Now the or logic, right? We can find a probability. We can also find a probability on the or logic as well. So if we want to find, for example, probability of x happening or y happening, it is equal to essentially probability of x happening, right? So if let's use the Venn diagram, right? Out of the whole probability, x or a would be this entire area. You can kind of see it like this. Therefore, if you just add up a, add up b, and over here there's a minor overlap because, well, when you put it on one on top of the other, it's overlapped twice, right? So we subtract away the overlap. So it's a probability of x, probability y, subtracting the overlap area, which is right here. So the logic to how to find or is pretty simple. That's how you can find like x or y. Okay, so let's understand a joint distribution by looking at an example. So in this table here, right? The probability of x equals to 0 and y equals 0 is 0. The probability that x is equal to 1, y is equal to 0 is 0.2. So you basically have a table that essentially tells you every combination. Now in this case, the probability we will use the and symbol, right? So based on this table, this is y equals to 2 and x equals to 1. Okay. So what is this? 1, 1. The probability of x equals to 1 and then y equals to 1. So it's this one here, right? So the probability is 0.1. So that's how you can read a table for discrete data. Now, when you're dealing with joint distribution, like you have x and y, a common question is, well, now that you have x and y and everything has to be x or y, how do you still have access to p of x alone and p of y alone, right? And the answer is yes. Yes. Having this implies that you have both of them. And the question is, okay, how do we go from here to either one of them, right? And this process is called marginalization. Marginalization. Now, if we using the table, right? Using the table, we see this table, right? We can still find the probability that of x for anything. So, or y. You can find the x or you can find y. So let's take the example for y. The probability that y is equal to 0, probability that y is equal to 0. All it is probability that y is equal to 0 and x is equal to 0 plus probability of y equals 0 and x equals to 1. So with probability of y equals to 0, there are two possibilities. It's either this one or this one. Therefore, the probability of y equals to 0 is the summation of both. Okay? You have, because this could happen or this could happen, and then you must sum them up. So therefore, probability of y equals to 0 is just a summation of all possible x's. So you keep y equals to 0 here, but you loop through all possible x's. So if x has x equals to 2, you will loop through and add all of them. Okay? And we tend to write them as probability of y equals 0 is equal to probability of y equals to 0. And you're summing up. So this summation for I equals to 1 to 2, so it's summing up all the possible xi's. And you're essentially adding up all the outcome. And this is called marginalization. And let's say you're trying to find p of x this time, right? Therefore, notice x is a constant. You would just plug x in here, but you're going to sum up all the possible y's. Conversely, if you're trying to sum y, you're going to keep y a constant, and then you're going to sum up all the x's. Now, this extends to continuous distributions. If it's just discrete, then you do the sum. If it's continuous, then you need to do the integral. So if p of x, right, you will need to sum up, doing the integral, sum up all the y's. Notice we left the x alone because it's p of x. And conversely, we want p of y, then we just take the integral and sum up all the x's. Okay? Right. Here's an example of marginalization. Let's say you want to find p of x is equal to 0. P of x equals to 0. I told you, you just have to sum up p of x equals to 0 when y is equal to 0, y equals to 1, y equals to 2. Right? So 0, 0 0.5, 0 0.1, voila. So that is the probability. And then probability, if we want to calculate probability of x is equal to 1, right? Then it will be 0 0.2 plus 0 0.1 plus 0 0.1, which is 0 0.4. So now we have the probability for p of x completely. We know p of x is equal to 0 is equal to 0 0.6. P of 0 equals to 1 is 0 0.4. They add up to 1, which makes sense. Should be 100%, which is 1. So this is the example, right? Now, if we were adding y equals to 0, here's the option. Well, then you have to add this up, right? And which is 0.2. All right, now I want you to quickly go over, try to calculate this yourself based on this table. All right, what is the OR logic? Remember, the OR logic is p of x plus p of y minus p of xy. All right, so that's the OR logic, and this is the AND logic. So pause the video, give it a try, and then we'll move on. So hopefully you should be able to get the answer. If you can't, make sure you go back and review it. Okay? All right, so now that we understand marginalization, the next concept we need to cover is called conditional probability. Now, probability of events change depends on some information. So if I tell you additional information, then the probability is going to change. So let's look at two particular situations. The probability that you would have a good date tonight. And second condition, probability that you will have a good date tonight, given additional information, that you will be talking about your ex the whole time. So I hope you will come to the conclusion that based on this additional information, the probability you will have a good date changes, right? If more information is given to you, then you can base on this additional information and essentially come up with a new probability. So this example essentially tells you that the probability of an event can drastically change based on some other information. And this is called conditional probability, which you can write as probability of x, and this symbol here is given. So if y is given, what is the probability of x? Or what is given x, what is the probability of y? So that's what this symbol means. So let's say x is whether you're going to have a good date or not, and y is the topic which you're going to talk about. So based on this situation, we will ask questions such as, what is the probability that x is equal, well, I should have used capital X, capital Y. X is a good date given that you talk about your ex, right? So again, this symbol here is given. And the conditional probability, how do we calculate this? We follow this equation. We have the joint, right? Probability of x given y divided by probability of y. Now, at a first glance, if this is the first time you've encountered conditional probability, it might not be obvious to you why this is the equation for conditional probability. So we're going to go over it really quickly. Conditional probability, right? So the equation for I just showed you, conditional probability, is the joint divided by the marginal. So remember what we talked about, the joint distribution is when they're together. The marginal is when you take one of them out. But this equation here, it's not an accident. Like there's a very logical reason why we use this equation. Given the probability shown on the right, if no additional information is given, then you have a total of 6 possible outcomes, right? 1, 2, 3, 4, 5, 6. So this is the original data. And if I don't tell you anything, no information is given, right? Nothing is given. Then you will just have 6 possible outcomes. And this will be your 100% of all possibilities right here. All 6 of them. Therefore, the total probability is essentially the summation of all 6 events, right? The summation of all 6 of them. However, if something is given, such as if I tell you that y must equal to 1, so that is given. So y must equal to 1. Well, if that's given, then the total probability of all the events that could possibly happen is these 2. Like this can't happen, this can't happen, this can't happen, this can't happen. None of these can happen because you were told this did happen. Y did happen. So you're stuck with this one. So this right here, probability y is equal to 1, is essentially the 100% of your probability. It's saying now the 100% is 0.6. So that's the 100% of the probability, which is the marginal, right? You're calculating the marginal of y equals to 1. So that's where this marginal comes in. Now, because y equals to 1, we only have 2 outcomes. Therefore, if we want to find the probability, that x is equal to 0, probability that x is equal to 0, given that y is equal to 1, right? Then what the probability of x happening is probability of x equals to 0 and y equals to 1. So the probability this would happen is right here. And then we need to divide it by the total probability, which is probability of probability y, right? So this right here, notice this is the joint distribution right here. And then this right here is the marginal distribution. Exactly what we describe here. Yeah, I'll give you one more example. Let's do another one. If we want to know the probability of x is equal to 1 given y equals to 1, okay? So now we given y is equal to 1. This time we want to find x is equal to 1. Well, then we just take this one, right? So probability that x is equal to 1 and y is equal to 1, and we're going to divide that by the total, right? The total is probability of y equals to 1. And voila, it should be 0.1 divided by 0.6. So that's how this come about. Like this equation is essentially what we just did. So when you look at this equation, you need to understand what's happening. When you are given something, right? When you're doing probability and something is given, what it essentially is doing is restraining all the possible outcomes. And after it restrains it, the 100% of the outcome is therefore smaller, right? This is 100%. And therefore, if you are only finding this out of 100%, you need 0.1 divided by 0.6. Or if you want to find this out of the 100%, then it's going to be 0.5 divided by 0.6. So it's that's how conditional probability is derived and comes about. So let's do a quick practice, right? Over here is a table of x and y. X is the probability you're going to have a good date or a bad date. And y is the probability of what you're going to talk about. You're going to talk about your x, you're going to talk about food, you're going to talk about travel, right? Depending on the topic you talk about, you may get different outcomes. So I want you to calculate, like pause the video and calculate what is the probability you're going to get a bad date in general, right? So The probability of a bad day, this is marginalization. What is the probability you get a bad day? Well, then you need to sum up all the possible outcomes. What is the probability you have a bad day given that you talk about your ex? Well, given that you talk about your ex, what is the probability you're going to have a bad date? Right? What is the probability you have a good date? Right? So what's the probability you have a good date? Based on this 0, I guess you can guess. And then what is the probability of having a good date given you talk about food or given that you talk about travel? Right? You can essentially come up with all these probabilities. And once you know the PDF, so the whole point is once you know the probability table, you can really make some really like choices what you should do. Okay. So, and lastly, I want you to answer why is the probability distribution or mass function so important. So, pause the video, give it like 5 minutes. See if you can do this. See if you can do this. I hope you can. Okay. I have written out the solution right here. Make sure you go over it and study. Okay. Or maybe I'll do one. I'll do one. Let's do one. Probability of bad day. Well, that's probability of bad day here. All the possible things you can talk about. So you need to sum up all the possible whys. All right. So that one is hopefully easy. What is the probability of a bad day given that you talk about your ex? So given that you talk about your ex, this is 100% of the probability now. Therefore, you want to find this divided by the 100% of your probability. So this is 0.2, and the 100% is 0.2 plus 0, which is 1. So the probability you have a bad day is 100%. Okay? Now the opposite of 100% is the good day, then 0%. So the opposite of 100% is 0%, so good date. And then you do the same logic, given that you talk about food. So let's say you talk about food. What is the probability you have a good day? Well, it's 0.5 divided by 0.6, which is 83%. Not bad. So food is pretty good topic to talk about. Or if you want to talk about travel, right? What is travel? Well, here's travel. What is the probability you have a good date? Well, 0.1, 0.2, 50%, 50%. So based on this probability, you probably want to talk about food and not much about travel, maybe a bit, and then just never talk about your ex. Like that's what the math shows you based on this table. Now, of course, I made up this table, so this has no bearing on reality. I could be just completely wrong. Like for all we know, maybe talking about your ex is a great thing. So this table, not real. So if you know the probability, like if you know all these probabilities, notice how essentially it allows you to make intelligent choices of what to talk about, right? And from this, you can imagine when you're making business decisions, when you're making like life decisions. If you have this table, you can make very, very logical choices. And this is why obtaining the PDF of probability mass function, it's so helpful. Now, conditional probability is only conditional if they depend on each other. So, remember we talked about this was the definition of conditional probability. And from the conditional probability, we can do a minor tweak. For example, I can just move this over here. So the join is now equal to the two of them. I mean, hopefully that logic is not too difficult. So right here, this is another way of writing the same conditional probability. But what is here is saying that the join is the conditional times the marginal. But conditional implies that knowing y tells you something about X. But what if knowing Y tells you nothing about X? Well, if it tells you nothing about X, then X essentially can ignore the Y, and P of X doesn't change. Nothing happens because Y doesn't influence X. And in those cases, right, when you can ignore this, we call them independent. X is independent because knowing Y doesn't change the probability distribution of X at all. And if that's the case, we can just ignore it. And after we ignore it, notice how it's just P of X, P of Y. That's it. So from this, you can understand the concept of independence. When variables are independent, the joint is just the product of the marginal. Okay? Joint is just the product of the marginal. And we call this independence. So you can show independence, right? If you can show that the joint is essentially the product, then there you have it. Now, following with this idea that we just did, that the joint is really the conditional, right? And that therefore this is essentially independence. So let's follow with the idea. Now, the same, we can yet do a different manipulation. This is right here what I just showed you, the definition of conditional probability. Well, if I combine this idea, which is the joint, right here. So here's the joint, and I rewrite the joint this way. So, so right here is probability, okay, right, I didn't actually write it out. So P of X, Y, notice it can be given X or given Y. So this could be P of Y given X, P of X, okay? So the two of them are actually equivalent. So take a second and realize that you can write it both ways. And if that's the case, now I can plug this one in here as well, which give us this. So this right here is called the Bayes rule. This not a huge logical leap. Essentially, probability of X given Y is the same as probability of Y given X times Y, because this came from the joint, divided by probability of Y. And believe it or not, like, this rule is really, really useful, because so much of machine learning can come from this. Like, for example, like sometimes you want to know the probability of Y given X, right? So voila, you can find it this way. All right, so let's practice using Bayes rule. Let's say in a neighborhood, 90% of the children are getting sick due to flu. So the probability of flu is 90%. Okay, so that 90%. And 10% kids are getting measles. Right? So these poor kids, and therefore 10% is 0.1. The probability of observing a rash given a kid has the measles is 95%. So probability of rash given measles is 95%. The probability of observing rash given the kid has the flu is 0.8. So rash given flu is 0.8. So what is the probability that the kid would A, develop a rash and have flu? So this is the joint, right? So how do we get the joint? And then develop a rash and have measles. So what is this probability? Or what is the probability that a kid would develop a rash in the first place? Okay? And more complicated. So this one, right, requires you to know the joint. So you need to use essentially conditional probability to get this. Same here. This one is marginal. So you need to know how to calculate the marginal. Have the flu given a rash. Right? So this one requires you to know the Bayes. So does this one Bayes. Okay, so try to remember this. Give it a try. See if you can calculate this. Okay, I have provided the answer here. Take your time, like study the logic and see if you can if you can reproduce this. Huh? Is this it? I guess this is it. Well, in that case, this is the lecture for today. I will see you next time.